A determinant of a matrix A is merely a condensed representation of a square matrix. Okay, and why are we talking about it? Because it's useful in variety of applications. So if we are talking about solving a linear system of equations, such as represented by this matrix equation right here, um, we want to know whether this matrix K is invertible or not in order to get the solution for displacement vector. Another example is coordinate transformation. So in finite element analysis, we generally map local to global coordinates for each element. And when you're dealing with large deformations, such mapping can often lead to a negative determinant, and which is a good indicator that something is going wrong in the analysis. So with that in mind, let's define what a determinant is for a 2 by 2 matrix. So let's have a matrix A, which is a 2 by 2, defined as A11, A12, A21, and A22. Then the determinant of a matrix A is simply the multiplication of the diagonal terms A11 times A22 minus the multiplication of the off diagonal terms, which are A12 times A21. With this in mind, let's talk about some of the properties associated with the determinant. If you were to take a determinant of the transpose of the A, would be the same as the determinant of A. Okay, now let's have two square matrices. A and B of the same dimensions. Then the determinant of the multiplication of two matrices A and B is simply a determinant of A times the determinant of B. Okay. If for any square matrix all the entry of a row are zeros, and this can be any row, or if all the entries of any column are zero, then the determinant of A is 0. Okay? And following this, we can then define a square matrix A is singular if and only if the determinant of that matrix is 0. Okay? Another word would be that this matrix is a non-invertible. So in the example of our system of linear equation, the matrix K times the displacement vector U is equal to some force vector F. If our matrix K is singular, meaning the determinant of matrix K is 0, then the solution for U is not possible. Okay? So another example of a matrix A where a matrix A is non-invertible or singular. Let's take 1, 2, 4, 8. Okay. So these two rows here are essentially the same, except that I can write 1, 2. This row is basically 4 times 1 and 4 times 2, right? So in such cases where either two rows are identical or one row is simply a scalar multiplication of the other row, in these cases, the determinant of that matrix is 0. Now for matrix A, for which determinant of A is non-zero, meaning it is non-singular, then we can define the inverse of the matrix A as such. And for which, if you were to take A inverse times A, will result in an identity matrix. Okay, and similar, you can reverse the order of the multiplication. A times A inverse will still result in an identity matrix. If you have two square matrices which are invertible, for two invertible matrices A and B, can write the inverse of A times B is equal to inverse of B times the inverse of A. Another definition associated with the inverse of a matrix is orthogonal matrix. Okay. A matrix A is orthogonal if the inverse of a matrix A is equal to the transpose of a matrix. Example of such matrix would be a rotation matrix. A rotation matrix is basically rotates the coordinate system. For example, if this was our initial coordinates x and y, and if we have a rotation matrix defined as R, this matrix R can then transform or rotate our coordinates by a certain angle, theta. Okay, that means that all the vectors that were defined in the original xy space are also rotated by the angle theta. So, for example, if this was my initial vector v, which would then be rotated to the new position v prime.